After studying this module, you shall be able to know about different X-ray techniques such as X-ray absorption, X-ray fluorescence and X-ray diffraction methods, general theory about origin of X-rays and interaction of X-rays with matter, instrumentation related to X-rays, application of X-rays and crystal tonography. A range of X-ray techniques and methods are in use, but we shall categorize all methods into three main categories. These are X-ray absorption, X-ray fluorescence and X-ray diffraction methods. Now first of all, we will know about X-ray absorption methods. These are analogous to absorption methods in the other regions of electromagnetic spectrum. Quantity of X-ray photons absorbed is considered to be a measure of the concentration of absorbing substance. X-ray absorption methods are useful in certain cases like elemental analysis and thickness measurements. As compared with other X-ray methods, absorption methods are the least used. Next is X-ray diffraction. Diffraction methods are based on the dispersion of X-rays by crystals. By means of these methods, we can identify the crystal structures of numerous solid compounds. These methods are extremely important as compared to X-ray absorption and X-ray fluorescence methods. Now next is X-ray fluorescence method. In this method, X-rays are produced by the fluorescence sample. By measuring the wavelength and intensity of the produced X-rays, qualitative and quantitative analysis can be performed. X-ray fluorescence method is non-destructive. Moreover, it requires very little sample preparation before the analysis is to be carried out. Each of the mentioned method is applied to different fields of analysis and depends upon different characteristics of the radiation. For example, X-ray absorption is employed to analyze imperfections in the inner structure of a material through which it passes. X-ray diffraction is applied to establish crystalline structure and X-ray fluorescence is utilized for quantitative and qualitative elemental analysis. All these three techniques are non-destructive. Now we will know about the journal theory. The origin of X-rays. The X-ray region of electromagnetic spectrum consists of wavelengths in the region of about 0.1 to 100 angstrom. For analytical purposes, the range of 0.7 to 2.0 angstrom is the most valuable region. X-rays are produced when high velocity electrons strike a metal target. The process of producing X-rays may be visualized in terms of Bohr's theory of atomic structure. An atom is made up of nucleus and numerous electrons. The electrons are arranged in layers or shell with the valence electrons in the outer shell. The different shells or layers of electrons are called the K shell, L shell, M shell and so on. Whenever a rapid moving electron impinges on an atom, it may knock out an electron completely from one of the inner shell of that atom. Following the loss of inner shell electron, one of the outer electrons will fall into the vacant orbital with the instantaneous emission of an X-ray photon. The energy of emitted X-ray photon is equivalent to the difference in energy between the two levels involved. The X-ray spectrum of a copper target consists of a few sharp and intense lines superimposed on a polychromatic background called white radiation. These sharp lines are due to emitted X-ray photons whose wavelength is equivalent to the difference in energy between the two levels involved and are characteristic of that material. Interaction of X-ray with matter. The X-rays can interact with matter in three ways: absorption, scattering and diffraction. Absorption. If a beam of X-rays is permitted to penetrate through a matter, it loses energy partly by scattering and some due to absorption. The absorption of X-rays means that the electron of atoms comprising the matter absorbs energy from these rays and get excited. Then these excited electrons emit secondary X-rays characteristic of those atoms. Scattering and diffraction. This shall be discussed in the following section. Fluorescence. If a sample is irradiated with an X-ray beam and it irradiates X-ray beams of different wavelength, the method is termed as X-ray fluorescence. The wavelength of X-ray fluorescence enable us to establish the identity of the element. The intensity of the emitted X-rays forms the basis of quantitative analysis. This method of elemental analysis is independent of the molecular structure of the element. The method is non-destructive in nature and requires very little sample preparation. Now we will see about the instrumentation. X-ray absorption, X-ray diffraction and fluorescence are the three main fields of X-ray spectroscopy. Only optical system varies in each case, although components of the equipment are the same. The main components are as follows. First, production of X-rays. The X-rays are produced as high velocity electrons impinge on a metal object. Approximately 1% of the entire energy of electron beam is transformed into X radiation. The remainder being dissipated as heat. Several types of X-ray tubes are used for producing X-rays. You can see a diagram of an X-ray source. Collimator. The X-ray produced by object material are randomly directed. They form a hemisphere with the target material at the center. The X-rays produced by the target material are then permitted to pass through a collimator that consists of two sets of closely packed metal plates divided by a small gap. The collimator absorbs all the X-rays except the fine beam that passes between the gaps. You can see the diagram of collimator system for achieving a narrow beam of X-rays. Monochromator. Monochromatic beams of X-rays can be obtained by two methods. 1. Filter. A narrow wavelength range X-ray beam is obtained by inserting a suitable filter in the path of wide range X-rays. A filter is made of a material which absorbs all but desired radiations. A nearly monochromatic beam of radiation is thus available. An interesting example is the zirconium filter, which is employed for molybdenum radiation. The next is crystal monochromator. A crystal monochromator is positioned in the path of X-ray beam so that the angle of reflecting plane satisfies the Bragg's equation for the required wavelength. The beam is split up by the crystalline material into the component wavelengths in the similar way as a prism splits up the white light into a rainbow. Such a crystalline material is called an analyzing crystal. The next component is detectors. The X-ray intensities are calculated and recorded by photographic plate, counter methods, scintillation detectors and semiconductor detectors. These type of methods depend upon the ability of X-rays to ionize matter and vary only in the subsequent fate of the electrons formed by the ionizing process. Photographic method. To record the position and intensity of X-ray beam, a cylindrical film is used. The film is developed after exposing to X-rays. Counter method. These are of the following types. Geiger-Müller tube. The Geiger tube is packed with an inert gas like argon and central wire anode is maintained at a positive potential of 800 to 2500 volt. When an X-ray enters the Geiger tube, this ray impacts the filling gas, causing it to lose an electron. This results in the production of an ion pair, and electron produced moves towards the central anode, while the positive ion moves towards the cylindrical outer electrode. The electron is hastened by the potential gradient and causes the ionization of a large number of argon atoms, resulting in the production of an avalanche of electrons that are travelling in the direction of the central anode. This results in an output pulse of 1 to 10 volt, which can be determined very easily by employing a simple circuit, as you can see in the diagram. Proportional counter. Its construction is analogous to a Geiger tube counter with lesser potential being maintained between the electrodes. A proportional counter is packed with a heavier gas like xenon or krypton. The heavier gas is chosen because it is easily ionized. Scintillation detector. In a scintillation detector, there is a large sodium iodide crystal activated with a small amount of thallium. When X-ray is incident upon the crystal, the pulses of visible light are emitted, which can be detected by a photomultiplier tube. Solid state semiconductor detector. In this detector, the electrons generated by X-ray beam are upheld to conduction bands. The current thus generated is directly proportional to the incident X-ray energy. Semiconductor detectors. When an X-ray falls on a semiconductor or silicon lithium drifted detector, it generates an electron and a hole in fashion analogous to the formation of an ion pair in a proportional counter. These detectors are of prime importance in both X-ray work and neutron activation analysis. Now let us see non-dispersive X-ray absorption method. In this apparatus, a tungsten X-ray tube is employed as a source which operates at 15 to 45 kilovolt. A synchronous motor driven chopper and an attenuator are placed between source and sample reference compartments, which alternately interrupt one half of X-ray beams. There are duplicate reference and sample cells up to 65 cm in length. If liquids or gases are to be analyzed, there are special arrangements for continuous flow of process streams. Both halves of X-ray beam are permitted to descend on a common phosphor coated photomultiplier tube, which is confined from visible light by a thin metallic filter. Now we will see the applications. This method is widely used to analyze any sample that contains one element markedly heavier than the other. However, some selected applications are as follows. It can be used to determine chlorine in hydrogen, plastics and hydrocarbons. It can be used to determine barium chloride in carbon and barium or lead in glass. Now we know about the application of X-ray absorption methods. The various applications are as follows. The first is qualitative analysis. This is based on the simple fact that there is a large difference in the mass absorption coefficient of one element from another. Quantitative analysis, amount of X-rays absorbed is directly proportional to the concentration of the element present. This characteristic is widely used to detect broken bones, impurities, segregation, etc. Now we see the X-ray diffraction method. It is commonly used for investigating the internal structures. Determination of crystal structure by Bragg's law. The X-rays are permitted to fall on the crystal structure. Then the crystal is rotated and X-rays are made to diffract from various lattice planes. The intense reflections are measured by Bragg's X-ray spectrometer and glancing angle for each intense reflection is recorded. Rotating crystal method. The rotating crystal method was developed by Shebolt in 1919. Powder crystal method. In this method, a single crystal is necessary whose size is not larger than microscopic dimensions. However, in the powder method, as little as 1 mg of the powdered material is sufficient for the study. The powder technique was devised separately by Debye and Scherer in Germany and by Hull in America about the same time. Now we see the application of X-ray diffraction. In determination of structure of crystal, the analytical application of X-ray diffraction are numerous. The method is non-destructive and gives information about the molecular structure of the sample. Perhaps its most vital use is to measure the size of crystal planes. Polymer characterization. Powder method can be used to establish the degree of crystallinity of the polymers. Annealing of metals. Well annealed metals are in ordered crystal form and give sharp diffraction lines. If the metal is subjected to drilling, hammering or bending, it becomes worked or fatigued. That is, its crystal becomes broken and the X-ray pattern becomes more diffused. Particle size determination. A range of X-ray techniques may be used to determine the size of particles or crystallites. Following are the methods for particle size determination: spot counting method, broadening of diffraction lines, low angle scattering. Application of diffraction method to complexes. Determination of cis-trans isomerism, determination of linkage isomerism, soil classification based on crystallinity, analysis of industrial dust, assays of weathering and degradation of natural and synthetic minerals. Corrosion products of metals can be studied by this method. Tooth enamel and dentine have been examined by X-ray diffraction. Effects of diseases on bone structure and tissue structure, identification of crystalline compounds. Now we see the fluorescence method. The principle of fluorescence method is as follows. The elements of the sample get excited by absorbing primary X-rays and discharge their own X-rays of characteristic wavelength. This procedure is called X-ray fluorescence. Components of the equipment. Instrumentation. The schematic diagram for an X-ray fluorescence system is shown in the figure. The filtered primary X-rays from the tube hit the sample and produce the fluorescence radiation characteristic of the elements in the sample. This radiation passes through a collimator and on the analyzing crystal. The wavelength is determined and recorded as the synchronized detector rotates in an arc around the analyzing crystal. Application of X-ray fluorescence spectroscopy. X-ray fluorescence is a method of elemental analysis used for qualitative analysis as well as for quantitative analysis. This technique is used in agriculture for the determination of trace elements in plants and food, detection of insecticides in fruits and leaves, and the determination of phosphorus in fertilizers. It is applied for direct determination of sulfur in protein, chloride in blood serum, strontium in blood serum and bone tissues. It is used for the examination of ores, tailing, concentrates and drilled cores, determination of silica in flowing slurries of ores, determination of lead in lead tin alloys. Other application includes the determination of additives in motor oil by determining barium, zinc, phosphorus, calcium and chloride, and the determination of lead or sulfur in gasoline. It is used in rubber industry for the determination of vulcanizing elements. Crystal tonography. There are numerous experimental diffraction techniques developed in current years, which help in analyzing the microscopical defects in a crystal. Most crystals are far from perfect and exhibit regions with somewhat differing orientations, or they may contain individual defects such as dislocations or faults dispersed throughout the crystal. Studies of these defects are important in understanding the nature of stress in metals, the nature and behavior of doped crystals used in transistors, the production of perfect crystals and other phenomena. Microradiographic techniques are based on absorption, and the contrast in the images is because of the difference in absorption coefficients from point to point. X-ray diffraction topography depends on the image contrast upon point to point changes in the direction or intensity of beams diffracted by planes in the crystal. One much used method of X-ray diffraction topography is known as Berg-Barrett method. The experimental arrangement is shown in the figure. The crystal is placed so as to reflect the X-rays at the Bragg angle for some plane. Geometric resolutions of about 1 micrometer can be achieved and single dislocations can be resolved. The dissimilarity on the film is owing to variation of the reflecting power due to imperfections in the crystal. Another method for X-ray diffraction topography is known as Lang method. A ribbon X-ray beam is collimated to such a small angular divergence that only the characteristic wavelength is diffracted by the crystal. Simultaneous movement of the crystal and film allows a large area of crystal to be investigated. Now let us summarize. A range of X-ray techniques in use are X-ray absorption, X-ray fluorescence and X-ray diffraction methods. X-ray absorption is employed to analyze imperfections in the inner structure of a material through which it passes. X-ray diffraction is applied to establish crystalline structure, and X-ray fluorescence is utilized for quantitative and qualitative elemental analysis. All these three techniques are non-destructive. X-rays are produced when high velocity electrons strike a metal target. The process of producing X-rays may be visualized in terms of Bohr's theory of atomic structure. The main component of the equipment are as follows: the production of X-rays, collimators, monochromator and detectors. Application of X-ray absorption methods are the qualitative and quantitative analysis also used to detect broken bones, impurities, segregation, etc. Application of X-ray diffraction includes analysis of industrial dust, assess the weathering and degradation of natural and synthetic minerals, corrosion products of metals, effects of diseases on bone structure and tissue structure, identification of crystalline compounds. X-ray fluorescence have application in agriculture for the determination of trace elements in the plants and food, detection of insecticide in fruit and leaves, determination of phosphorus in fertilizers. X-ray diffraction topography depends on image contrast upon point-to-point changes in the direction or the intensity of beams diffracted by planes in the crystal. Method of X-ray diffraction topography are the Berg-Barrett method and the Lang method.